So in this video, I'm going to be talking about the effects of zeros on the transient response of a linear system. And the reason I'm covering this is because it doesn't seem to be covered in any of the textbooks that I've read or in any of the online control system lectures that I've been able to find. And this seems really quite bizarre. Um, so if we've got a typical system, so let's say we've got a normalized transfer function, so 1 over 1 plus s over omega naught, or if you prefer alpha instead of omega naught, then this will perhaps make you feel a little more comfortable, or even alpha over s plus alpha. These all mean the same thing. It's just that this one is normalized, and it's easier to visualize what exactly is going on. So if you were to plot the response on a Bode plot, you'd be able to say immediately, okay, it starts at 0 dB, and the magnitude plot goes to omega naught, and then rolls off at minus 20 dB per decade. So this is my personal favorite form for the transfer function of a single pole, and that's what I'm going to be using in this video. But it's exactly the same as this alpha over s plus alpha form. So don't be scared by it. So we know the response to a simple first order single pole, so 1 over 1 plus s over omega naught. We know that the step response, so if we apply an input step, which is shown in red, we know that the transient response, which is shown in green, will look something like this. It'll be an exponentially decaying, or it'll be like a step that has been smoothed, sort of. So this looks like the equation for this is just 1 minus e to the minus omega naught t. So as t becomes very large, this term becomes very small, and we just approach the value 1. And so this is assuming a unit step. Uh, well, okay, that's sort of been beaten to death, I think, in basic linear systems analysis. So what happens when we add a zero to it? So let's say we add a zero at omega z, and we've got our pole at omega p. So how does that change the transient response of the system, and specifically the transient response to a step? Because we can immediately get the transient response to an impulse from that. And in my opinion, this is just much more intuitive to look at. So if we apply a step of unit amplitude, we'll see something kind of interesting. And uh, I'm going to start by saying let's assume that omega z is equal to omega p. What would we expect to see? So basically, we'd expect these zeros and these poles to cancel out each other so that the step response to a step is just, well, it's a step. So if omega z equals omega p, we expect to see a step. So if omega z is slightly less than or omega p, or omega z is slightly greater than omega p, we might expect to see the same kind of characteristics, this sort of instant response uh, at the origin, combined with some other kind of response. And so, what exactly is that? Um, well, if we do the math, and so we just take the inverse Laplace transform of this transfer function, 1 plus s over omega z divided by 1 plus s over omega p, where we've got a pole at omega p and a 0 at omega z, or strictly speaking at minus omega z, uh, then the inverse Laplace transform of this is just 1, as we'd expect, minus e to the minus omega pt. So this is interesting, first of all. The transient response, the exponentially decaying part, is determined only by the pole. And then 1 minus omega p divided by omega z. So this is the complete step transient response. And I'm going to plot it out for omega z not equal to omega p to sort of make this much more clear. So if let's say that omega 0 or omega z is greater than omega p. So in that case, let's say omega z is what? What do you guys want? Let's say it's twice omega p. So then this reduces to 1 minus e to the minus omega pt, 1 minus omega p over omega z is 1 minus 1 half, or that's just 1 half. So 1 minus 1 half e to the minus omega pt. So at t equals 0, the step response actually jumps up immediately to 1 half, or t equals 0 plus. The step response immediately jumps up to 1 half, and then it starts to decay just like a normal pole would, with the same exact omega p. So by adding this 0, we're canceling part of the pole. So we're sort of making the step response more like a step. And so this was for omega z greater than omega p, or the 0 is faster than the pole, if you will. But what if omega z is less than omega p? Well, in that case, let's say that omega z is 1 half omega p, so the 0 is slower. Then this equation instead becomes 1 minus 2, or I guess, sorry, if that's omega z equals 2 omega p, then we'd get 1 plus e to the minus omega p t, because 1 minus 2 over 1 is just, the negative of that is just 1. So we'd get 1 plus e to the minus omega pt. So the response would actually look like this. It would overshoot the step by an entire, actually the entire amplitude of the step in this case. So at t equals 0, plus, the value is 2. So here the value was 1 half. And then it'll start to decay with the same time constant as before. And the time constant is entirely determined by the pole, which is interesting. So we can see that by adding a 0 to our system, depending on the relative frequency of the pole and the 0, we can effectively cancel out part of this step response. We can make it more instantaneous. But we see that if we try to cancel it out too much, then the step response actually overshoots, and we still get the same effective settling time. So it still takes the same amount of time as for just a single pole to settle than it does for a pole and a 0 to settle. So for this reason, adding a 0 to your transient or to your system isn't always the best way to improve its transient response, because if your 0 is much different than your pole location, you could actually get a worse transient response. Or if your system doesn't allow these kind of overshoots, it can only handle such a range of voltages, you could destroy your system. So you shouldn't just mindlessly add zeros thinking that they will make your transient response better. So if we want to just summarize, this overshoot has a magnitude of 1 minus omega p over omega z. And similarly, this undershoot, or the amount of response that's left for the pole to do, also has a magnitude of 1 minus omega p over omega z. And these really should be the magnitude of each of these, because it can be negative. So we see that the important part about the adding a 0 is the ratio of the 0 and the pole. Because if the 0 is so let's say the 0 is at infinity, so that's nothing but the transfer function of a single pole system, then this term, omega p over omega z, is 0, and our response reduces to the original response. So you just plug in omega p over omega z equals 0, and you get the initial response. So it's this ratio, omega p over omega z, that determines what our response will look like. And you can immediately get from that what the height of the either undershoot or overshoot will be in your transient response. So let's just make that clear. So in this case, this is 1/2. In this case, this is 1. And you can just calculate that immediately if you know the ratio of the pole and the zero. So in the next video, I'm going to talk about the effect of a single zero on second order systems. So underdamped, critically damped, etc. systems. And the reason I want to do this is because if you know how zeros affect a first order response and you know how they affect a second order response, since you can always decompose a linear system into those two, you will know how zeros affect any linear system, or at least that's my claim. So hope you enjoyed this video, and I'll see you next time.